Hello, I'm going to talk about our DLP controller. We created a DLP class in C and we used I2C class that uses the Linux driver, and we're going to control it from the ARM processor. This is a demo application that will look from the internal images of the DLP. In this part, I'm going to show you how to program the FPGA to control the DLP with the parallel interface. First, we need to program the FPGA. Once it is programmed, we execute the I2C configuration of the DLP. And over there, we can see the
I'm going to show you how we connected the DLP with the FPGA. So how you can see, this DLP is a cape for a BeagleBone Black. So with our PCB, we want to use the HPS of the FPGA with the DLP. This will increase the adaptability of the board. For create this PCB, we have used KiCad for do the schematic and Altium. This is the final PCB that we have created. The main goal of this part of the project is calculate the angle of rotation for compensate the projection with the DLP. So we have created an hardware-software integration. For do that, we have in the part of the software an em016 class that corresponds to this emu. An emu is a device that integrates accelerometer, magnetometer and gyroscope. In the other hand, we have an I2C class for the communication between the HPS and the emu. It's known that for describe an 3D movement, we have to talk about pitch, yaw and roll. In our case, we are interested in the roll that corresponds to the y-axis. So, if we have the emu in this position, we have a acceleration of 9.8 Gs that corresponds to minus 90 degrees. If we rotate the emu, we have a 9.8 Gs approximately and 90 degrees. This value is not uniform. It can be improved with a filter in a future.
In this part of the project, I'm going to show a little demo that will swipe through all the colors of the DLP with the FPGA that we have in hand. So the first thing I'm going to explain is the functional blocks. So we have a synchronization circuit that handles the BGA timings, and then we created a binary counter that a 32 binary counter to cover the 24 bits that we have in the DLP. However, we don't need a binary representation. We need a decoded representation so that when the counter says 7, instead of having the 3 first bit on, we will have the 7th bit on the on position. We will follow this diagram provided by the Texas Instrument, where we can find the data and we translate this data into colors by this mapping. However, this representation is not right because this is for the general circuit provided by Texas Instruments, but we do have a DLP evaluation module which uses this representation. This was a big challenge for us to decipher because it was not written in any part, but the representation, as you can see here, is first 5 bits red, the next are green, next blue, well, and you follow this diagram to achieve the representation swiping. So what I'm going to do now is to load the FPGA soft image. Once it's done, I will configure the DLP through I2C, and over there we can see the increasing of the colors with the color swipe. I'm gonna turn off the light so you can see more clearly. You can also see here on the LEDs that the counter has a binary representation with the LEDs that corresponds to the bit lighting up in the screen. So to also check that, we have used the analog discovery to check that each input that we are sending is the one that we are receiving. So we have a visual aid in the FPGA with LEDs, and we are getting sure that that data is correct with this type. As we just have 16 bits here, the other 8 bits are, we cannot measure them, but they are non-significant bits, and because of the representation on the screen, we know that they are right. But that's how we prove that our model is done correctly. This part of the project is going to prove the automatic tilt correction in the development of the project that we made. We coded this in C and are going to use the graphical part of LXD in the Linux distribution to output the image data through HDMI. I'm going to show you the components of this system. Here we have a DLP evaluation module, and underneath we have the DE10 Nano connected through HDMI.